So let's continue for our first part of thermodynamics. So last week, so we just learned the first law of the thermodynamics. Yeah? What is first law of thermodynamics? What's the first law of thermodynamics? Very end. Yeah. What's your name? Okay. What's the first law of the thermodynamics? So you've been here last week? You didn't attend, yeah, okay. We can easily see, yeah. Okay, white cap. What's the first law of thermodynamics?
Work, physical heat, and the overall energy is
80%. What's the first law of thermodynamics? Delta U is always 0. What's that mean? In the system, no, 50%. Yellow. Yeah, so what that mean? Delta U of universe is 0. So energy of universe is always constant. That's actually first law of thermodynamics, okay? We are talking about the universe. And of course, inside the universe, we have the system and the surrounding. But total energy change, which is sum of system energy and sum of surrounding energy, that's always constant. So energy in the universe is not increasing or decreasing, it's always constant. That's the first law of thermodynamics. And then in the inside of this energy, I mean, they could have different kinds of form of energy. And two of the most common, actually, most well-known form of energy is first one is the heat and the other one is work. So heat and work exchange each other to keep the same energy in the universe. That's the first law of the thermodynamics. Okay? Good? So among the three laws, we already learned the first law. And today we're going to learn the second law and the third law, okay, of the thermodynamics. So second law of thermodynamics is, I mean, you already know the entropy. And also third law of thermodynamics is related to the entropy. So we're going to derive the function for the entropy, and then we'll try to understand how this entropy is related to the so-called irreversibility of the process or randomness of the system. Okay, that's what we want to learn today. Okay, so this will be 2. So basically, we're going to learn definition of the entropy. Entropy is, we used S, capital S, typically. Okay, so before actually we introduce entropy directly, we have to introduce terminology about reversible process and irreversible process. Okay, so any kind of the natural process is irreversible process. So typically any kind of chemical reaction, any kind of the event going to the certain direction. So one direction. It's not the other way around. So that's the irreversible. So we're going to the only one direction. Reversible means we are going to the forward and backward, without any actually the friction. But if you actually go to the only one direction, that's irreversible because we cannot turn it back. Okay. So let's look at that irreversible and reversible process. So what's this actually means? So one of the most famous diagram we can show the reversible and irreversible process is like this. So let's assume we have some sort of the energy well here. So this is energy state with process here. Okay, so this is kind of energy. We don't know which energy it is, but so, or we can just assume this is kind of the hill. So this is kind of valley, and this is two mountains on the side. And then if you put actually a ball here, okay, the ball naturally try to go down to this position, the minimum energy position, okay? So it can go down, and then also if you have the other side here, I mean the other ball, it can go down, so it's actually going to the negative actually direction of the process, but it will stay here. But so this is possible, but if you want to do it, this is impossible without adding some additional energy. So if you don't put any additional energy, naturally this ball to going down and then keep each position at the minimum energy point here. So we go this way, but cannot go back. This kind of process is called irreversible process. So it's not reversible, okay? And compared to that, reversible process is like this. So let's assume I have the energy level is almost same, or let's assume I have very, very small difference in terms of energy level here, okay? And then I have the ball here. I'm moving this ball to here. I'm moving back this ball, or the other way around too. So both of them, both process is possible. So of course, I mean, this one should be extremely small, so you don't have any, the ball doesn't feel any difference in terms of height, for example, or in terms of energy. Then this ball can move this way or this way. If there's no friction energy here, then ball can move any position without changing of its energy. Okay? Okay? So it can go both direction. And this one, we call it reversible process. Okay? And reversible process, in terms of thermodynamics, we call this one as thermodynamic equilibrium state. So equilibrium state. Okay? So typically when you have the thermodynamic equilibrium state, your reactant and the product have certain level of energy, and then the energy is same, that's why it's equilibrium. Okay? So you always actually learn the actual thermodynamic in terms of, let's say, okay, is this reaction going to the forward or backward? And then also, if you're in the final state, equilibrium state, then you can go to the forward and backward simultaneously. It's the same level of energy. Okay, your reactant energy, your product energy is same. That's the reversible process at that final stage. Okay, but when you're actually talking about, okay, A plus B becomes C, for example, now I'm going to actually toward a certain direction, so it's going to the forward reaction or backward reaction. That's the kind of irreversible process. Okay, so in terms of the natural process, all the natural process, if you are not adding any additional energy for the system, if all the natural process is actually the irreversible process, it's going to the certain direction. Okay, and then when it actually arrives to the equilibrium state, then it's now reversible process. The final state is reversible process. So ongoing process is typically irreversible process, and we call this one as spontaneous reaction. Spontaneous process. Okay, so this is the difference between the reversible and irreversible process. Then why are we actually learning the reversible and irreversible process? Because this one gives the idea for the entropy. Okay, so second law of thermodynamics starts from actually reversible process and irreversible process. So when you have this kind of irreversible process, then we have to think about, okay, during the irreversible process, is there all the energy we are talking about? I mean, the system energy is Q and W, yeah? And this Q and W in the irreversible process and the reversible process is different. Okay? So even I start from here and then there, so in terms of first law of thermodynamics, whatever route you are using, the energy difference between the first state, final state, is independent of your route. Yeah? And however, depending on the route, you can have different amount of work or different amount of heat can be involved. Okay? So if I take the route for the reversible process, if I take the route for the irreversible process, the final answer in terms of energy is same. However, the amount of work, the amount of heat involved during the process could be different. And that actually gives the idea for the irreversibility and how much irreversibility you have in those kind of process. That actually detecting that is counted as a entropy. Okay, so we actually try to develop the equation for the entropy. Okay, so then in many cases, okay, so we can think about it in this way. So this energy, what is this energy? Is this the heat, or is it work, or is it really the energy like the U? Okay, so in terms of energy here, this energy means U. Okay. So far we learn. The only energy we learn is U. So we can you can say that this is the energy as a U. Okay? But a lot of the process, when you actually measure it, you cannot really directly measure the U. Okay? But you can more directly measure the Q, heat. Heat you can measure it because you see that, okay, heat from here to here, you can actually put the detector, you can see how much heat is moving. And that's actually basically just coming from the temperature difference, so we can easily see that. Okay? And many actually chemical reactions, so for example, so let's assume in chemical reaction, so for example, A plus B become, for example, C plus D. And in terms of heat, there's the two kinds of reaction we can think about. So one is, and when you're actually doing this one, you can have heat is generated or heat is observed during this chemical reaction. Okay? When this delta Q is positive, so it means when I have the chemical reaction A plus B, I have A plus B here, and I make a chemical reaction, and then during the chemical reaction, it produces C plus D. At the same time, it produces the heat. Okay? So this kind of chemical reaction, we call it exothermic reaction or exothermic process. So it generates heat. So it releasing the heat during the process. That we call it exothermic. Okay? And you can have also delta Q could be less than 0. And this one we call it process. So in the beginning, actually, when people develop the thermodynamic law, they want to actually find a certain thing. And then one of the things they want to find out, okay, so whenever you have this kind of chemical reaction, when the delta Q is exothermic, so if I have the chemical reaction, and then it produces heat, so it means it looks like it's losing the energy. So I have energy level, high energy level, and then when it produces C plus D, it becomes low energy level. That's why energy is coming out from there, yeah? So delta Q become positive. It's an exothermic reaction. So exothermic reaction looks like irreversible process. It's going to it's dictating, okay, what's the direction of chemical reaction, yeah? But in reality, it's not always like that. So typically, in the most of time, when delta Q is positive for the chemical reaction, this is natural process. Because naturally, we want to release the heat. So for example, if I have liquid metal, if I leave it naturally, it becomes solid. During the solidification, it has to release the heat there. So in order to actually you melt it, you need the heat to heating up. And when it's cooling down, it releases the heat. That's most of the natural processes like this. Most of, it's not 100%. That's actually a problem. So when people actually think about, okay, what kind of criteria, what kind of energy criteria we are used to dictate direction of the chemical reaction, people are thinking about this reaction here first. Okay, Q could be the good indicator to say that, okay, this reaction going to forward or backward. But in reality, yes, about 95%, yes, it is true. When delta Q is positive, you are more or less irreversibly going to that direction. Okay, natural process. But however, it's not 100%. So we cannot use this criteria to dictate actually how this chemical reaction going to the forward or backward. Okay? So this is one of the actually thing we always talk about when you have reversible and irreversible process. So unfortunately, delta Q equal to 0 doesn't mean that it's direction of irreversible process. So it doesn't really tell what's the direction of irreversible process, what's the chemical reaction, the direction of the chemical reaction. And about 90%, as I told you, working like this, but another 5-10% is not really following this rule. So we cannot use this one. And that's why eventually we're going to derive Gibbs energy. So when the Gibbs energy of system is going down, that means that's the actual direction for the chemical reaction. Okay? When the reactant and the product, when you compare the Gibbs energy of reactant and the product, if the product has lower Gibbs energy, then that chemical reaction should happen irreversibly. Okay? So that's the reason we're actually using the Gibbs energy as a criteria for the direction for the chemical reaction. But unfortunately, Q is not. Okay? So because Q cannot be used, so that's why we actually want to develop Gibbs energy. In order to develop the Gibbs energy, we need entropy, enthalpy and the entropy. Okay, we learned the enthalpy last week. So anyway, so this is the one of the things we have to learn. So now, okay, so how we actually develop then the entropy. Okay, so many people actually try to explain what's actually what's meaning of the entropy. But one of the most well accepted concept to really explain the entropy is the heat reservoir, the system I'm talking about now. Okay, so let's take, so this is not very important, so let's just clean up again. So 2. So regeneration of heat from work. So this is actually basic concept of the second law of thermodynamics. This is happening in the irreversible process. So this is the very conceptual experiment. So like let's take this kind of the system here. Any thermodynamic book actually using this example to explain this one. So let's take here, this is, so for example here, I have piston here. So there's the P external, so pressure applied in the outside. Here I have liquid. And there's the gas phase here inside of this piston. And then this is heat reservoir, okay? So kind of heat tank here, and I have liquid water here, for example, water, and I have vapor here, for example, okay? So, and then I have certain temperature and pressure, of course. On this system, I have certain temperature and certain pressure of the gas, okay? And then I want to actually take this piston out. Then it means my gas, and then I want to keep the same temperature and same pressure inside of my system. So this is my system here, and everything else is surrounding. So this part here, this is my system. All the rest is surrounding, okay? So I want to expand this one, so I want to do the work. Okay? But during the work, I want to maintain the same temperature, same pressure in the system. Okay? So you think about it. So PV equal to nRT. So in order to keep the same temperature and pressure of the gas, but I want to expand my volume, then the only way you can actually maintain temperature and pressure is to generate more gas phase. So you have to fill up actually the empty place here by additional gas. So it means I have to evaporate my liquid to make a gas during the work. Okay? And also you have to think about this one. Okay, in order to then evaporate my water to the vapor, I need heat. Yeah? So I have to add heat to evaporation. Yeah? So that heat, in order to maintain same temperature, that heat should be coming from the surrounding. Okay, that's the system we are talking about here, okay? Okay, so in the end, I'm going to make this one. So my piston was originally here, and then this is my final position. So same P external is applied, and so here my liquid is still there, and my gas phase, and then my temperature. So this one is delta V, new volume, yeah, and my temperature and the pressure here. So this is temperature initial state and pressure initial state, and let's take this one as the temperature of the final state and the pressure of the final state. Okay? Okay, and then what I want to do is like this. So in order to actually doing this work, according to the PV work, we can have two different kinds of work. We can have reversible work and irreversible work. So that's the thing I want to actually introduce here. So let's take, if I have this is P and this is volume. So volume is increasing here. So this is my initial pressure and initial, so this is initial state. Okay? And then my final pressure is same. So this is even my final pressure. Volume is increasing, of course, yeah. Then I can have two different kinds of process. So I can have like this. So in the beginning, I have P1 pressure, but I dropped my pressure very quickly outside here. P external is dropped. So this can expand it very quickly. And then expand, and then going back. So my pressure is maintained as the same. Okay? So typically this is P external. Okay? I can make this kind of process. Okay? And this is, for example, irreversible process. Because according to this diagram, so I have initial pressure internally. So I have system pressure here. I have external pressure. I decrease the pressure very quickly. Then piston move out. Yeah, it's a natural process. Irreversible. You cannot do this way. You can only move out. Yeah, so it's irreversible process. Okay, and depending on how big it is, you can have much quicker expansion. Yeah, how big difference between the internal pressure and the external pressure. If your internal pressure is same as the external pressure in the beginning, if you decrease your external pressure very, very quickly, or very, very big difference, then the tendency to move the piston out is much bigger. The tendency for irreversible process, it's bigger, depending on this difference here. Okay? So this one dictates degree of the irreversibility, basically. Okay? And compared to this one, let's take another route. So let's take, okay. So I'm changing this P external very, 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 I make a very, very small decreasement of the P external. So the difference is very small, but it's just slightly smaller. So it just moves very, very, very slowly, but you can end it up in the end to this position. Yeah. So let's just take it's almost same. So like this one, the difference is really infinite. It's infinitely small. Then it moves almost same actually direction without changing the pressure. And let's take this one as a reversible process. It's possible, yeah? Because I have very small difference, it's moving out, and then if the pressure is slightly higher than moving back, but I mean moving out, moving back, moving out, moving back. But in the end, you can reach to this final state. Okay? So we have two different processes, but the end, the result is same, but the two different processes. Okay, so let's look at actually the how much energy, so how does the energy internally is changing depending on these two processes. Okay, so let's take reversible process now because it's easy to understand. So one, reversible process. I mean, this is just the energy U. So let's go back to the actual first law of thermodynamics. So delta U of a system, reversible. REV means reversible process, is delta Q of reversible process minus delta W of reversible process. Is it okay? Just. And then, now let's take 2. Now delta U, so irreversible process. So irreversible process. So delta U of system irreversible equal to delta Q of system irreversible minus delta W irreversible, yeah? But if you actually compare these two, delta U of system reversible, delta U of system irreversible should be same. Because the U is state function, which is independent of the process. It's only depending on the initial state and the final state. Both of them, initial, final is same, yeah? So delta U should be the same. So these two equations say that, okay, delta U of system reversible and delta U of system equal to same. So that give delta now Q reversible. So this and this one same. So let's just subtract each other. Then delta Q reversible minus delta Q irreversible equal to this one, delta W reversible you can write it in this way. Is this okay? Is it okay? And this is higher than 0. Is it okay? So energy of a reversible process, energy change, total energy change, the system energy change of reversible process, irreversible process, same. Because U is state function, which is only depending on your initial condition and final condition. Because initial and final is same, exactly same. Same temperature, same pressure, same volume. Okay, same system. And so if you just equate that together, then if you just subtract these two equations, 1 and 2, then you can get delta Q reversible minus delta Q irreversible equal to delta W reversible minus delta W irreversible. And if you look at this one here, work is P dV, yeah? Integral of the P dV. And if you look at this one, reversible amount of work is this one, irreversible is this one. So this difference here is delta W reversible minus delta W irreversible, which is always positive. Is it okay? So now this is okay. In terms of all this equation, that makes sense. But what this means, that's actually very important. That's very important. So let's think again, okay. So let's go back to our original process, okay. So I say that, okay, in order to expand this one without changing any pressure, so in order to expand my volume without changing temperature and pressure, the only way we can do this one is we have to evaporate more water to the vapor. That's the only way. Yeah. So that means I need a certain amount of heat from the surrounding to evaporate my liquid to the gas phase. Yeah. That's delta Q basically. Am I right? So that's very strange. Okay, so now let's do it in this way. If you all do this one of the very strange thing is, okay, delta Q I need for the system. Or what system need delta Q, or let's say this is delta Q total amount of heat I need for the system. This is for heat of evaporation. Over my liquid phase from gas phase to fill up that actually the additional volume. Okay? So this is the amount of heat I need in the system. Yeah? And however, the amount of heat we need, the amount of heat we get from the surrounding, from the two systems, two actual process is different. Yeah? So let's take actually this amount of heat which we need for the evaporation is same as delta Q reversible process. When the reversible process, we have a certain amount of heat is taken from here to here. So this is delta Q basically. We're getting from the surrounding to make evaporation. Okay? So let's assume that's the same heat. So delta Q reversible is the amount of heat we need to evaporate water to the gas phase to fill up that actually the additional volume. Okay? This one, so this is for the reversible process. But when you actually look at this one, during the irreversible process, the amount of heat we receive from the irreversible process is delta Q irreversible, yeah? So I receive the delta Q irreversible from the, so here. So this is reversible process, I'm receiving this one from the surrounding. And for the irreversible process, I'm receiving this delta Q irreversible amount of heat from the surrounding. That should be used for evaporating my liquid to the gas phase. But this is smaller than this one. So in terms of evaporation, you cannot make evaporation you need for really filling up that gap. Am I right? Whether it's reversible or irreversible process, it doesn't matter what the process it is. From the water point of view, I need this amount of heat to make me to evaporate. Yeah? That should be the same heat. But in the reversible process, we receive all those heat from the surrounding. That's good. From irreversible process, in the irreversible process, we receive only part of that heat from the surrounding. But I need additional amount of heat somewhere inside the system to compensate that difference and make actually all the gas, all the liquid to evaporate. Am I right? It's conceptually, this doesn't make sense. This value is not enough. And so the amount of heat we need is so I need this additional amount of heat. So this is irreversible process. So this one, I get it from the heat reservoir. So basically, I'm getting this one from surrounding. So in this case, heat reservoir. So I'm getting this amount. But how about the other amount? Because it should be same amount, so you can equate in this way. This heat should come out somewhere. This heat, if you look at it here, okay, this minus this is same as this minus this. Okay? I mean, coincidentally, this is same quantity. And if you think about actually your process here, okay, so potentially my system was supposed to do this amount of reversible work. Yeah? But however, my system only did part of that heat. I have potential, like 100% potential to do the work, but because of irreversible process, I'm using only 80% of that capacity to work. Then the other 20%, where it's going? That actually coincidentally matching with this one. So people think, okay, so let's take it in this way. This amount of difference of irreversible work is going to the heat. So instead of using that capacity to make a work, that work is change its form and then become heat. So it's internally generating the heat because of irreversible work. It makes sense? Is it okay? So this is coming from the heat. So we call it regeneration of heat from work. And of course, in this case, irreversible work. Because of irreversibility of the process, instead of doing the old capacity for the work, part of that is converted to its form to the actual heat, and then stay inside of system again. So in terms of system energy point of view, it's the same. Yeah. So instead of doing work, I actually take it as a heat. So in terms of system, my initial and final, my final energy state is same. However, because of irreversibility of the process, instead of doing the work, maximum work, I'm actually doing part of that work, and then the other part of the work, remaining part, is changing its form and then supplying the heat inside of system. Okay, that's what we call it, so-called regeneration of the work to the heat. Regeneration of the heat from the irreversible work. Okay, so if you think about now, okay, so this irreversible amount of work here. So this is interesting point now. This one, as I mentioned, if you have more and more irreversible work, so that means this difference becomes bigger and bigger. So you'll have bigger and bigger difference between reversible amount and irreversible amount of work. So if my process is more and more irreversible, then the amount of work, the amount of heat which is regenerated from the work become bigger and bigger. Okay? Is it okay? So irreversibility is somehow kind of measured by actually the amount of the work or amount of heat regenerate from the work. Okay? You good? Yeah.
I can understand that the delta Q irreversible is not enough for the evaporation.
Mm-hmm.
Can you describe it one more time?
Can you explain what?
Can you describe it one more time?
One more time. Okay. So let's assume this way. So because of expansion of this volume, so PV equal to nRT, we know the P and we know the T and we know the V, then we can calculate how many moles of the gas should be evaporated. Yeah. So let's assume I have 0.5 moles of water should be evaporated from 25 degree to the 25 degree of the gas phase or whatever, or 100 degree to 100 degree of the gas phase, for example. Then in order to actually evaporate that, I need a certain amount of energy. That amount of energy we just define as this one. So heat of evaporation, total energy I need in the system, total heat I need in the system. And then in the reversible process, let's assume that amount of heat is only coming from surrounding. Because there's no heat generating inside the system. So heat should be coming from the surrounding, yeah? So let's take this one as same amount as that. I mean, this heat is same actually the amount of heat as the what is needed for the evaporation of the 0.5 moles of the gas phase or liquid phase to gas. And however, compared to that one, now irreversible process, the amount of heat we're getting from the surrounding, which is delta Q irreversible, this is smaller than delta Q reversible. Yeah? But however, for the evaporation, we need the same amount of heat. So there should be additional source of heat in the system or surrounding. But surrounding, this is surrounding. So then additional, actually, the source of the heat should be inside of the system. Okay? But you cannot see anywhere. There's no heat generation process here. The only thing we can think about now is from those equations, the work which is not carried out by actually the system should be changed its form to become heat. So instead of doing work and heat is just one of the energy form, yeah? So two forms of energy, heat and work. So work and heat can be exchangeable, okay? Instead of doing maximum amount of work, I do the part of the work, and then the rest of the actual remaining work is used just for increasing the temperature of the system. That's Q. Okay? The concept is important, not equation, the concept. So reversible process is the maximum, in the reversible process, we are taking maximum amount of heat from the surrounding. Okay? In reversible process, we are taking part of the heat I need for the system from the surrounding, and the rest of the heat is generating inside of the system. Okay? So irreversible, when you have the more and more irreversible of the system, more and more irreversible process, the amount of heat regenerate from the work is become bigger and bigger. So it means system don't do the work as much as it can do. Okay?
So you mean the situation which is the mixture of reversible and irreversible process, the heat needed to evaporate the water is from the surrounding, which is equal to heat reservoir, just like the reversible process. And the remaining is from the work we've done to the system, right?
Yep. So take part of them from surrounding, part of them from internally. Yeah. But if you accept this one, we're going to see very, very surprising thing now. Okay, so let's take it in this way. And then, now, okay, in terms of then total energy. Okay, so now, for the reversible process, so delta U of system and delta U of universe delta U of system plus delta U of surrounding, yeah? Okay. And so delta U of system is delta Q of system. So when it is reversible process, this is reversible, minus delta Q. So, and then delta W of reversible process. Am I right? And then you have U, same thing. Delta Q of reversible minus delta Q, delta W, reversible. So this is minus now, this is plus, because it's from the surrounding point of view. So system point of view, I received this amount of heat from the surrounding, but from a surrounding point of view, I lost this amount of heat to the system. Yeah, and this is 0. Okay? Now, in terms of now, irreversible process. So delta U of universe, and this is 0, of course. Delta U of system. Delta U of system is similar thing like this. Delta Q irreversible plus minus delta W irreversible plus here. Now minus delta Q irreversible plus delta W irreversible this should be 0, of course, here. It should be same. But this is different. So delta Q for the system, I receive only delta Q from the reversible, from the irreversible process. I only take it from the irreversible process from outside. But however, the real heat I need in the system is higher than this one. This is this amount. So the Q of irreversible in the real system for the irreversible process and the Q which actually surrounding gave to the system is different. So this and this one, in theoretically, if you really, kind of the, let's say, break down all the heat you need of the system and the surrounding, this for the system minus this which surrounding gave to the system is different value. That's actually the difference here. So system needs still reversible amount of heat. Okay, but surrounding gave only irreversible amount of heat. So heat for the system and the surrounding is different. And then that amount is actually covered by this irreversible work, which actually received by the system and which is given by the system and received by the surrounding. But however, in terms of total, when you just sum up together, it becomes still 0. Okay, anyway, forget about this one, but the important thing is this one. Okay, system. In terms of system, you have something different. Okay, now let's define the new quantity here. So 3. Now really second law. So we want to define the new quantity. That's delta S. This is what I want to actually now define. Okay. So this is a very interesting concept. I mean, so people look at, okay, there's irreversible work. Heat is generating from the irreversible work. Okay. And they want to actually quantify this one to the, they want to use this one to quantify the degree of irreversibility of the process. Okay. So basically, when you have more bigger irreversibility, you have more heat generating from the system, yeah. And irreversible process is natural process. So we can dictate from that irreversibility, we can dictate, okay, this process can go to the forward or backward. We can tell the direction. So that's actually a very good idea. Okay, so we try to use this, so if I can tell whether this system is irreversible process, and then if that is positive irreversible process basically, then I can say that that is the process I'm moving. So that's the direction of the process. So I can tell now chemical reaction going to forward or backward. Okay. So in order to actually then, okay, use that actually the irreversible or degree of irreversibility, and we have to generate a new terminology. That's actually the entropy, terminology called entropy. So entropy, you saw the actual S for a long time, entropy. Entropy is degree irreversibility. And also, we call this one degree of randomness. So, one of the actually the simplest actually the way to define the y, how does the entropy equation should be like this. If you actually measure that entropy is degree of the randomness or degree of the irreversibility, we use this kind of the thing. So let's assume I have here heat reservoir. So let's assume this is T1 temperature. Okay? And then, okay, basically this is temperature. And then let's take here T2 and then another T3. So this is two final state, okay, of my system. Okay? And I mean, this is the process basically. Process number 1, process number 2. So this is process. Okay? So it's conceptual actually, the diagram here. And during this one, let's take this one, amount of heat is Q2, Q3. Okay? So, if you think about it, okay, so irreversibility of the process. So irreversibility of process. Okay, I have a higher temperature here, heat reservoir. Heat should come from the higher temperature to the lower temperature. It's the other way around, it's not working at all. So heat should move from the higher temperature to lower temperature. So surrounding, if I want to give the heat to the system, surrounding temperature should be higher than the system temperature. Okay, so this is surrounding, and this is two of the my system, two case of the my system. Okay, so if the temperature difference, if the temperature T2 is lower, so let's assume this is 1000 degree, 500 degree, 100 degree. So degree of the irreversibility, this one should be bigger, yeah? Because I want to, the temperature difference is bigger, so I have to give the more heat more quickly to make that equated with my surrounding. Okay? So I have more chance to give more potential. And then, in the same way, if you have the difference is bigger, then you have more energy going in, more heat going in. Okay? So people try to actually equate these two quantity, Q and the T, to dictate degree of the irreversibility. And that's this one. Delta S, entropy change of a system, equal to delta Q, the amount of heat I'm supplying. So when you have the more heat is supplied, you'll have more irreversible possibility. If you just look at this way. And then, if your temperature is lower, you will have more chance to actually make a more, irreversible process. The T is system, basically. From system point of view, Q from the surrounding, Q of the system, and the T, Q and the T. And in the Q as a linear way and T as inversible, the reversible way, this actually detects the irreversibility of the system. Okay? So that's why actually people define in this way. Entropy change is heat divided by T of the system. Is it okay? So entropy change of the system is the delta Q of the system, or delta Q, which is coming from surrounding, divided by T of the system. Okay? So this is the definition of entropy. And the original idea for defining this way was how we quantified irreversibility of the system. And so S was standing for the irreversibility, degree of the irreversibility of the process. Okay? So then if you have this one, now if I make a derivative of this one, so ds, entropy change, infinity is small actually the range of the process, then dq over the t. T is fixed. Yeah.
Can you explain about the connection between entropy and temperature?
Entropy and temperature. So this is my heat reservoir, and this is my system temperature. If the system temperature is lower and lower, so when T is smaller and smaller, you'll have more irreversible process. Because the difference is big, so I have to do more heat. I have to give the heat more quickly. So if the temperature of the system and surrounding is similar, then the speed for the actually giving the heat is very slow. Yeah? I mean, there's almost no difference. So wait a minute, I'll give you slowly. Okay? But if this guy is very, very hungry, very, very low temperature, and my surrounding temperature is much, much higher, then, I mean, he's begging actually the food. And you have to give that food by the heat, yeah? So the temperature of the system is very important. One of the quantity which can tell you whether actually you are more reversible or less reversible, less irreversible, more irreversible or less irreversible. And as I mentioned, heat reservoir should be always higher temperature. So the system temperature is always lower than heat reservoir temperature. So the temperature is lower and lower, you'll have more chance to have the more irreversible process. Does it make sense? Okay? So delta S is defined by this way. This is just definition basically. People did it in this way. And then if you do actually the derivative, ds, because T is constant at the given temperature, then dq over the T. And this is very interesting. Now, dq is, when it's constant pressure, this is Cp dt over the T now. Is it okay? dq is the Cp dt here at constant pressure. And it's constant volume, Cv dt, of course. Okay? And this delta S, then integral of Cp over the T dt from initial temperature to the final temperature. This is very important. So, do you remember we have delta H when it's constant pressure, we can actually define in this way. So delta H and delta S. So Gibbs energy, we know H minus Ts. So we know the both quantity now. Okay? So now, let's look at actually this entropy a little bit further. I know it's a bit confusing, yeah? we want to just introduce concept for the entropy. And that's why we actually did this heat reservoir with the system and the expansion of the piston by the amount of heat. And then we also defined irreversible, actually, the heat and regeneration of heat. And then we are heading for this one now. The last part is now this one. So if I define actually the second law of thermodynamics in this way, now let's think about this one. Delta S of a system is delta Q of a system divided by T of a system, yeah? Is okay? And then same way, delta S of surrounding equal to delta Q of surrounding T of surrounding. And then let's assume T of system, same as T of surrounding. Okay? And now we are going to this one. Delta S total. So it means delta S of system plus this one. So we have two different answers. So for the reversible process, this delta S of the system is this one, delta Q of reversible divided by T. So we say that this is same as T. Let's assume then delta S total is system plus surrounding, and delta S of system, we know that actually the system entropy, so the system heat is the same as reversible amount of heat, yeah, of the T, plus surrounding. So surrounding, which actually give the heat to the system, it actually gave that reversible amount of heat to the system, yeah. So this will be minus delta Q zero. So this is when it's a reversible process, we can actually say in this way. When it's now irreversible process, now you have difference. Irreversible process. So delta Q of irreversible process of the system point of view, I need the same amount of the energy as a reversible process here. Is this okay? So the Q I receive from surrounding and the Q I generate inside the system by the regeneration of the work. That's the amount of heat I need in the system. So system heat is same. And whether it's coming from outside or whether it's generated inside, yeah, the total of the system heat I need is same. So this is delta S of the system in the irreversible process. However, now delta S of surrounding point of view, surrounding doesn't know the system, whether he did the reversible process, he don't care. Yeah? The amount of heat he gave to the system is only the irreversible amount of heat. Yeah? That's from the heat reservoir, from surrounding. Yeah? So this is minus delta Q of irreversible over T. This one is higher than 0, yeah? So this term cancels out. This is positive. Okay? So delta S total equal to delta Q reversible minus delta Q irreversible over the T. And this is always higher than 0. When it's reversible process, this is same, so it's 0. When it's irreversible process, it's higher than 0. Okay? And Cis total means universe. Is it okay? This is actually second law of thermodynamics. This is second law of thermodynamics. This is second law of thermodynamics. So let's think about this way now. Okay, so in terms of equation, it's like this. Second law of thermodynamics. Entropy of universe is always positive, always increasing when you have any kind of irreversible process happen. It makes sense? So irreversible process is natural process, most naturally spontaneous process. Any kind of spontaneous process generate entropy of universe. Make sense? It's not system, unfortunately. It's not the system we are talking about. It's a universe. That's actually a bit difficult. So second law of thermodynamics is very nice. However, it's not very applicable in reality. So let's recap again. So when you have second law of thermodynamics, it's basically like this. Delta S of total universe delta universe or delta S total, and this is let's assume process. Whenever you have process, it's increasing. So let's assume this way. So we have the process. If I change the process, imaginary process, if I change process, delta of universe is changing in this way, then it means this one is increasing direction, yeah, of the universe, entropy of universe. This is spontaneous reaction. It's a natural process. It's irreversible process. I'm doing this way. I want to increase my entropy. And when it reaches to the maximum here, it means I'm moving this direction, it doesn't change the entropy of universe. So this point here is equilibrium state, reversible process. And then here, it's also going to this direction, yeah? It cannot go decrease the actual entropy. There's no process which can decrease entropy of the universe. It's not happen. It's not natural process. Okay? So delta S of universe is always increasing whatever you have process. And then when it doesn't change anymore, it means now I'm reached to the equilibrium state. Okay? It's a very nice law. Now at least I have measured. Okay, so it's good. Second law of thermodynamics can tell you what's the direction of the process. Yeah? If the delta S of universe is increasing, that means my process is going that direction. Okay? However, it's not applicable in reality because I want to look at only this lecture room as my system, but I have to take care of everything outside simultaneously. It doesn't make sense, yeah? I have to spend more time to counting entropy change in the outside than inside. Okay? So it's a very nice law, general law, which can tell actually the reversible process, irreversible process, and whether actually my reaction is really happening in this direction or not. But unfortunately, this entropy, second law of thermodynamics containing both system value and the surrounding value. And unfortunately, the surrounding value is unlimited amount we have to count. So it's not applicable in reality. Conceptually, yes, very good. However, it's not really applicable in reality. Okay? This is second law of thermodynamics. So first law of thermodynamics, energy conservation of the universe. It's very conceptual too here. And it's not only for the system, it's entire universe. Second law of thermodynamics, same thing. It's entire universe entropy is always increasing with irreversible process, natural process. So I can tell the now direction, but unfortunately I have to count both system and the surrounding. So it's not very applicable. Okay? That's why we actually develop, we are continuously actually moving to the direction to develop the Gibbs energy function. In the end, we are developing Gibbs energy function to count only system energy. And then by using Gibbs energy of system, we can tell, okay, whether this reaction is going forward or backward. Okay? So first and second law. It's a very nice law, unfortunately, very difficult to apply in reality.